Hello, everyone. Welcome to the HPL seminar this week. It is my pleasure to introduce today's speaker, Olivia Bruce. Olivia received Bachelor's of Science degree in 2015 at Queen's University, where she worked on a research project addressing the effects of fatigue on double underturning, one of jump ropes techniques. Then in 2016, she came here to the University of Calgary to start her master's course in kinesiology under the supervision of Dr. Brent Edwards. During her master's, she primarily worked on tendon mechanics. So specifically, she examined how surface and footwear modification would affect to Achilles tendon strain during vertical jump landings and quantifies the relationship between tendon strain and accelerometer measures. Right after she achieved her master's degree in 2018, she continued her academic career by starting PhD course in biomedical engineering at the same university here. Her current research project is focused on statistical shape and intensity modeling of the tibia and fibula, which is related to her talk today. Also, she is planning to graduate next year. Aside from her work career, she also mentions that she used to compete in jump rope. Also, recently, she started teaching herself painting with watercolors. So Olivia, if you have any plans for a painting exhibition later, please let us know. Today, she will be giving a talk entitled as Statistical Shape Modeling, Estimating Participants' Specific Tibia and Fibula Geometry from Anatomical Landmarks. All yours, Olivia.
All right. Thank you for the introduction. All right, so let's just jump right in. So musculoskeletal modeling is a commonly used tool in biomechanics. You can use it to calculate things like inverse kinematics, inverse dynamics, muscle forces, and joint contact forces. So when you're creating these models, you need to define bone geometries. And this can be done using medical imaging, so usually CT or MRI. And this provides accurate, individual specific bone shape. But this approach is really costly in terms of time and money. It involves radiation exposure for your participant if you're using CT. And also access to the scanners can be limited, or for some research institutions, they just don't have access at all. As a result, it's much more common to isometrically scale a generic model. And this approach is easy and accessible, which is why it's done so commonly, but it doesn't capture individual variations in bone shape. So some of these variations could be related to factors like age and sex. So as an example, periosteal expansion occurs over time and with age. And there's also some evidence to suggest that it occurs to a greater degree in older men than in older women. So other differences in tibial geometry related to sex include some greater protrusion of the tibial tuberosity, more acute curvature, and larger condyle size in men compared to women. So when some of these variations were accounted for by using a sex and size matched reference model, joint contact force estimates were substantially closer to values for an image-based model when compared to a generic model. So another approach that could be used to predict bone geometry is statistical shape modeling. Now an SSM calculates the average shape, which is shown in the figure here in red. It also calculates principal components, which represent variations in shape, and those are shown in blue. And this is calculated all for a sample of shapes. So among its many applications, statistical shape modeling can be used to predict bone shape from partial medical imaging data, 2D radiographs, and even anatomical landmarks. So there are a few studies that have developed SSMs for the pelvis and bones of the lower extremity and predicted shapes from anatomical landmarks. Two of these studies included the tibia and fibula. So Zhang and colleagues found substantial improvements in geometric accuracy for the pelvis and femur but less so in the tibia and fibula in an SSM when compared to using isometric scaling. One of the reasons could be that the SSM that they developed was combined the pelvis and both lower limbs together in one shape model. Or it could also be because they only used 3 landmarks on the shank, so there might just not have been enough information for accurate reconstruction. Now, Nolte and colleagues focused on the tibia and fibula, and they also did the femur, and they observed improvements in accuracy compared to isometric scaling. But most of their results, they only reconstructed with one principal component. Now, both studies trained and tested their models on a group with a wide range of ages. So they did this to include lots of variation in the model so that the model could be applied to, say, any healthy adult. But what if you're interested in a more specific group? So many of the biomechanics studies and lots of the projects here in the HPL are focused on young adults. And there may be less variation in shape within this group. So would an SSM trained and tested on only young adults provide better results? And would it be significantly more accurate than isometric scaling? And that led me to the purpose of this study. So primarily, I wanted to create a statistical shape model of the tibia and fibula for healthy young adults. With that model, I wanted to evaluate the accuracy of reconstructions from bony landmarks and compare that accuracy to the accuracy from isometric scaling. Once I had the model, I also wanted to look into sex differences in bone geometry and also to look at reconstruction accuracy for a group of older adults to get an idea of how robust the model was for application to an entirely new population. So this is an overview of my workflow. I started with 41 CT scans. So we had 22 females and 19 males. They were all recreationally active and 18 to 23 years old. So pretty typical of the type of people that you're going to get in biomechanics studies here in the HPL. So once the tibia and fibula were segmented, surfaces were registered and aligned. And then a principal component analysis was used to calculate the statistical shape model. I also went back to the CT data, exported those surfaces and digitized landmarks, which were then used in combination with the shape model to reconstruct participants' bone geometries. So let's go through step by step with a bit more detail. So again, I started with CT data. I segmented out the tibia and fibula, and surfaces were created and exported to MATLAB. I selected one participant as the template to which all others were registered. So the first step in the registration was that I used a coherent point drift algorithm. And what this algorithm does is it translates, rotates, scales, and then locally deforms the point sets of the participant to match the template. And from there, I could identify corresponding points between the participant's surface and the template surface. Those points were then isolated from the participant's original point set, so undeformed. And then a generalized Procrustes analysis was used to align all of the participants' point sets to each other. So what you end up with is a set of registered point clouds. A principal component analysis is then applied to that set of registered points to obtain a shape model. So again, a statistical shape model gives you an average shape and principal components, which represent variations in shape. To reconstruct a new shape, you take the principal components that you're interested in using, you multiply them by a score or a weighting factor. If you're using more than one principal component, you sum those, and then you add all of that to the average shape, and that gives you your new shape. So in the figure on the left, the red represents the average shape, and the blue represents the average shape minus 3 standard deviations multiplied by a given principal component. So once I had the shape model, I went back and digitized landmarks, and I did this manually on each participant's CT-based surface, as well as the average model from the SSM. So I created 2 sets of landmarks. The first set included 9 landmarks, and those are circled in red. And these landmarks could be palpated. So in theory, this set could be identified with motion capture markers. The second landmark set included 14 landmarks. So I used all 9 landmarks from set 1, plus an additional 5 landmarks that were in non-palpable locations. So I couldn't use motion capture markers to identify them, but maybe they could be identified using less intensive imaging techniques. And I thought that these locations circled in blue would give me more information about the shape that might increase accuracy of my reconstructions. So once I had my landmarks and my shape model, I could start reconstructing. So I used a leave one out analysis. And by that, I mean I removed one participant from the set of registered points. I then generated the shape model and then reconstructed the geometry of the participant that was originally removed. So it wasn't included in the original model. And then I repeat that for all 41 participants. So to reconstruct with the SSM and from landmarks, the average shape is deformed along the first 8 principal components and also translated and rotated to best match the landmarks. And this was done using a BFGS algorithm where the objective was to minimize the squared distance between reconstructed landmarks and the participants' landmarks. And you can see an example of a reconstruction in the figure on the right, overlaid on top of the CT data. You can see it's a pretty good reconstruction. I also wanted to perform isometric scaling to give myself a reference for what's normally done. So I calculated a scaling factor, and the scaling factor was the distance between the lateral malleolus and the fibular head markers, between the average surface and the participant surface. And this was done to simulate what's commonly done where segment length or the distance between the lateral knee and ankle markers are used to scale the tibia. So now I have 3 reconstructions for each participant. And those reconstructions were aligned to the CT-based surface for each participant using a rigid iterative closest points algorithm. 3 error measures were then calculated: root mean square error of the distance between surface points, maximum error, so the largest of those distances, and Jacquard index. So Jacquard index is a measure of similarity, where 0 means that the 2 shapes don't overlap at all, and 1 means that the 2 shapes are identical and perfectly overlap. So these figures are showing heat maps that I've created to help me visualize some of the errors across reconstructed shapes. So the 3 on the left are different reconstructions of the same participant, and same for the right, but for a different participant. So you can see on the left that if the participant's bone shape was already very similar to the average, there wasn't much difference between reconstruction methods. But when the participant's shape was different from the average, SSM landmark reconstruction worked better than isometric scaling. And you can see in the set on the right here that the darkest red areas, indicating the largest errors, occur in the isometric scaling reconstruction, particularly at the medial malleolus and in the diaphysis of the fibula here, and that those errors are reduced in the shape model reconstructions. And on average, we saw that same pattern. So SSM reconstructions were more accurate than isometric scaling. Root mean square error was 9 to 15% better. Maximum error was 12 to 15% better. And Jacquard index was 4 to 5% greater in shape model reconstructions compared to isometric scaling. And looking at the absolute values, SSM reconstructions had really good accuracy. So RMSE was 1.5 to 1.6 millimeters, which is quite good. And the maximum error was about 5 millimeters, so half a centimeter at worst, on average. Now, isometric scaling accuracy in this study was also very good, especially when you compare it to previous studies. So those Nolte and Zhang studies that I talked about in the introduction that also looked at tibia and fibula reconstructions. They reported RMSEs of 3.87 and 3.67 millimeters for isometric scaling. The root mean square error in this study is 2 times smaller at 1.78 millimeters. So the difference in age ranges could explain this. So the population of young active adults in this study was likely more homogeneous in terms of bone shape than a population spanning 20 to 90-year-olds. And if you have less shape variation between an individual and the average shape that's scaled, that would result in lower error. Now looking at just the shape model reconstructions, using 14 landmarks did provide improved accuracy compared to using just 9 landmarks. So root mean square error was reduced by 7%, maximum error by 6%, and Jacquard index was increased by 1%. But reconstructions from 9 landmarks still resulted in better accuracy than isometric scaling. So RMSE was 9% better, maximum error was 12% better, and Jacquard index was 4% better. And so this indicates to me that it could be possible to use the shape model with 9 palpable landmarks to reconstruct tibia and fibula geometry from motion capture markers and get better accuracy than isometric scaling. So switching gears a little, once I had the model and it knew that it reconstructed geometries really well, I wanted to see if any principal components differentiated between sexes. So I took the principal component scores and compared them between males and females using t-tests and found that 3 principal components were different between sexes. So principal component 1 corresponded to overall scaling. So the male tibiae were larger than the females. Principal component 4 was shape differences. And so these are a bit more subtle. To me, what principal component 4 looks like is that there's a longer length and larger cross-sectional size of the proximal half of the tibia in males compared to females. And for principal component 7, the size of the proximal and distal epiphyses were larger in males. The curvature of the diaphysis was a bit more acute in the males, and tibial tuberosity was more prominent in the males compared to females. And so this figure, the scatter plot here is just showing the principal component scores for the female subjects, which are the red circles, and the male subjects in blue squares. And so there is overlap, quite a bit of overlap between the principal component scores for PC4 and PC7. But the females tended to have more negative scores for both principal components, and the shapes describing some of the extreme values of those scores are shown in magenta. And the males tend to have more positive principal component scores, and so those shape differences are shown in blue. Okay. So finally, to examine the robustness of the statistical shape model that I developed, I applied it to a new population. So Dr. Andrew Mikowski provided access to a set of 10 cadaveric CT scans. These subjects here were a mix of males and females, and they were 71 to 98 years old. So I used the same procedure as before to reconstruct geometries using the landmarks and the shape model that I developed from the young adults. And we saw a pretty similar pattern in the older adults compared to the younger adults. So shape model reconstruction performed better than isometric scaling. The root mean square error and maximum errors were about 25% lower, and Jacquard index or volume similarity was 14% better in shape model reconstructions compared to isometric scaling. Now comparing the old and young, the errors were larger compared to the younger group in the older group, but absolute values are still quite good, on the order of values that were reported in those previous studies that we talked about, and still 25% better than isometric scaling for root mean square error and maximum error. So one of the reasons that isometric scaling performed quite poorly is that circumference was underestimated throughout the length of the tibia and fibula. And the figure on the right is showing the participant surface from the CT in red, and underneath that in blue is the isometrically scaled average model. And this image is very typical of what I saw across all 10 of my participants in the older group. And this could be explained in part by periosteal expansions, the outward expansion of the periosteal surface over time with age. So I think it's important to note here that generic models that are commonly used to define bone geometry in musculoskeletal models are usually defined from cadaveric data of older individuals. So for example, I have here that the TLEM model, it was defined using an 85-year-old male. So if scaling a young adult tibia results in underestimation of circumferences in the tibia and fibula, then scaling an older tibia to a young adult would probably result in overestimation of circumferences for that younger participant if you're doing isometric scaling. And that's going to result in greater errors. Now, the shape model was able to account for some of that variation, and it reduced the error in circumference. So the figure here that I have is showing two reconstructions, and these are reconstructions of the same individual. So I think it's the great visual that shows how the isometric scaling, this bone is much thinner compared to the shape model reconstruction. And we can see here with the very dark red on the heat map showing larger errors, especially at the proximal and somewhat in the distal ends of the tibia in particular. And so when the shape model was used, it was able to account for that and provide a better estimation of bone shape. And this gives me some confidence that the shape model that I developed was robust enough to be applied to other populations. So I've talked a lot about how statistical shape modeling improves accuracy of bone geometry predictions, but going back to the very beginning of this presentation, what does that mean for what we get from musculoskeletal models? Well, we know that bone geometry influences muscle moment arms, muscle forces, joint contact forces, and even finite element predicted stresses and strains. So there's a recent study that found that joint contact forces and tibial stresses were up to 30% different during walking between scaled generic and an image-based model. And there's another study that showed that joint contact forces were 50 to 67% more accurate when they used a sex and size match model. So they were using an atlas-based approach when compared to a generic model. So the statistical shape model method that I'm using here would provide additional improvements in geometric accuracy over that atlas-based approach. And so I would expect to see even greater accuracy in joint contact forces than was observed in that study. But more work is needed to quantify exactly how much the specific improvements in geometric accuracy using the shape model will affect outcome measurements from musculoskeletal models. So to summarize, the statistical shape model that I developed estimated participant-specific tibia and fibula geometry with very high accuracy and improved accuracy compared to isometric scaling in both young and older adults. Now, when we looked at the isometric scaling, using the model specific to the population of interest substantially improved accuracy of isometric scaling. And while errors were larger in the older adults compared to younger adults, the statistical shape model was still able to account for geometric variation in the older adults, resulting in lower errors compared to isometric scaling, and providing confidence that the model is robust enough to be applied to some outside populations. Now, what I'm working on right now, moving forward, is incorporating density into my shape models. And once I have that worked out, I can start looking at questions like how do variations in geometry and density affect finite element predicted strains? Can tibia and fibula shape and density distribution be predicted from anatomical landmarks? Do I need partial imaging data? And how do errors in geometry and density influence musculoskeletal modeling measurements, as well as finite element model output measurements? So I'd like to thank those who were involved in this project, my committee, my group members, and my funding. And I'm looking forward to everyone's questions.
Thank you very much, Olivia. So before we start the question and discussion period, I would like to kindly encourage you to turn on your camera during the discussion period if you feel comfortable with it. I think it would give us more active discussion. Thank you for doing it. So if you have any questions for Olivia, please use the icon raise hand button. So if you go click reaction icon at the bottom of your Zoom screen, you will see the raise hand button with other icons there. If your Zoom does not show you that button's there, then please feel free to send me a message via Zoom chat, then I'll call on you when it's your turn. Now the floor is open for the questions. Yes, John, please go ahead.
Thanks for the talk. I'm one of those people who does not have access to imaging, and so this is super exciting to see. I have two closely related questions, so I'll just ask them both at the same time. One of them, I noticed you used 8 principal components. Do you know what the distribution of, like, what percentage of the variance that accounted for, and like what it would look like if you used more versus less? And then also a number question, do you feel like the accuracy of your model would get better if you had more subjects? And did you have any feeling for what the, like, what's the minimum number of people to get good, good principal components?
Sure. Okay, so I'll start with the first question. 8 principal components corresponded to 96.2% of the variance. And I did do reconstructions with sort of 1 to 8 principal components, and the accuracy generally improves as you include more principal components, which is what I'd expect. You're accounting for more variation that's included in the model. As far as I do expect that the model would get better as I'm including more individuals. I don't think 41 is on the large side for what I've seen in the literature, but it's still not really enough. So I would think that we'd be looking more like in the hundreds, ideally, but the more the better. There is I used an analysis to figure out how many principal components I should use. And it looked at how stable the principal components were as you added more and more people into the model. And so the number of stable modes hadn't stabilized yet, or it hadn't plateaued. So I didn't have if I added more, that would in theory improve the model. But it also tested, so it's why I landed on 8 was the number of modes that were stable. And then beyond that, they were the analysis was telling me they were unstable, so that I probably shouldn't be looking at using them. Did that get everything you're asking? Yeah, great.
Olivia, actually, I also have a question for you. It's a more overall generic question, I think. So I might have missed, but would there be any reason why you choose to reconstruct tibia and fibula model? Would that be somehow related to your future study that's calculating the bone loading? Just curious about that.
Yeah, well, so one of the applications could be running studies or focused on, Brent's lab does a lot of work on stress fractures. The tibia is the most common site for stress fractures. And so that's one of the reasons we chose the tibia. It's an area of interest for me, and I think it's very common bone that you want to look at for running studies. And so that's where we landed.
Also, I actually have one just minor question. So you've worked on the leg bones, but do you think your SSM model could be also used for other bone reconstruction as well?
Absolutely. So It's been used for, statistical shape modeling has been used for a variety of bones, as well as joints. So there's a few papers out there for the fibula, sorry, not the fibula, the femur, the pelvis. There's people doing shape modeling of the hand bones, the foot bones. I've seen ones for the spine, as well as the knee, and the shoulder joint. So it has applicability quite broadly. And you can do it for shapes that aren't actually bones either. I think people have done it for other organs as well.
Thank you. I see Anquan, you have a question for Olivia?
Yes, Olivia, thanks for the nice talk. It's a very interesting topic. I have a question about one aspect of your analysis. If you actually look into the contour shape of the tibia plateau, because there's a lot of interest in building the knee joint, human knee joint. So I understand that you look into the overall shape of the tibia and the fibula, but how about the shape of the tibia plateau?
Okay, so the model that I've developed you could look specifically at the tibial plateau if you wanted to. I think for applications to the knee, there's a few papers out there that have specifically looked at the knee joint. So just the proximal tibia and the distal femur. And sometimes they include the patella, but not always. So I think if you were looking at, you could apply the shape modeling approach to just say the proximal portion of the tibia if you wanted to, just to look at the tibial plateau. Or you could do it on the whole bone and try to see if there's differences in the principal components there, but that would be more of a visual comparison.
I see. So another question about the terminology. The statistical shape model is different from atlas-based model, is it correct? So atlas-based model is a isometric scaling model?
Yeah. So as I understand it, the atlas-based model would be like you'd have a variety of reference models that have different characteristics. So you would say, okay, I want a young adult female with a height of 170 centimeters, and you'd find the closest match within that atlas to the reference bone, and then use that, and then isometrically scale that.
Don't actually take the shape of the say a specific subject, but you just based on the characteristic of a subject, you choose from a library of model.
Yeah.
Okay.
Or at least that's what was done in that one paper that from 2019 that I was talking about. Okay, could be that I've got the terminology wrong.
Thanks.
I see Ropi, you have a question for Olivia?
Yes, my question will be related to the landmark choosing. In your slides, you're showing you're having two groups, one with 9 landmarks, one with 14. And would you mind explaining a little bit more about how did you choose the location of the landmarks? Is it done by any software algorithms, or did you did it manually?
Nice. So I created a little script in MATLAB that would display the surface, and then I would manually select each point on the surface, and then it would, I could move it around to make sure it was in the right spot. And when I was happy with it, I could export that point into a variable.
I see. All right. Thank you. Yeah, I'm good. Thank you very much for your answers. Mm-hmm.
I see Benno, you have a question. Please go ahead.
Thank you for the presentation. You are in the PhD program, is that right?
Yes, that's correct.
And what is the topic of your PhD?
So my PhD is focused on statistical shape modeling of the tibia and fibula, with the goal of...
The shape modeling is the topic, or are you going to apply that to something?
Yes, so we're going to apply that to some running data and look at how the errors from using those shape models affect the outcome from finite elements models, affect the strains from finite element models during running.
So it's primarily a methodological topic.
Yes, the idea is to develop and test the tool, which could later be applied by the lab or myself to other problems or applications.
Your supervisor will use it then.
Yes.
Good.
And I will use it, I think, eventually.
To do what?
Oh, so I think Brent's probably going to use it to look at strains during running for applications to, or looking at stress fracture risk.
So is
And
that
I
part
think
of your thesis?
Hmm?
Is that part of your thesis, or is that afterwards for a postdoc? Or?
I think that's going to be afterwards. Right, the thesis needs to, there's a lot to do in the development of the model, and we need to test the model to make sure that it's that it works and that it's relevant and that it's valid. And then once we have that, we can apply it. Some of the application I might do as the third study, but we'll see how that goes.
Okay, thank you.
I still have a few more minutes for a couple more questions. Yes, Walter, please go ahead.
Thanks, Olivia, for a nice talk. I have a couple of questions. You know, I was very interested at the end there when you said that you would like to combine your shapes also with the bone mineral density. And, you know, as people get older, my understanding is, you know, you lose kind of bone mineral density. And I was thinking, is the expectation that the bone changes partly shape because bone mineral density might change? So bone mineral density gets less, the bone is weaker. Do you accumulate more bone to kind of compensate for that? Do people think that there is an interaction between shape and bone mineral density, or is that unexplored?
So I think it's somewhat unexplored in the tibia. There has been some work done in the spine that has looked at, you know, as you age, yes, you lose density, and there does seem to be some geometric compensation for that. And there does seem to be, at least the paper that I can remember from this, there seemed to be greater compensation in men than women, which is interesting. So I do think there might be some compensation, but it definitely hasn't been looked at in the tibia. Someone might have started looking at it in the femur, but I haven't come across that research yet.
The other thing I was thinking is when you do the shape predictions, and maybe not everything is always explained, might potentially muscle size or muscle mass play a role. So you have two individuals that are similar height and kind of similar build, but one is very muscular. I intuitively would expect bigger and stronger bones. Is that correct? Or has anybody looked at muscle mass size interactions with bone shape, or again, is that relatively unexplored or not known? Or
I think if anything, there might be some work out there that looks at relationships between muscle strength or size and maybe cross-sectional properties or density. But the shape modeling approach is somewhat new to biomechanics. And by somewhat new, I mean maybe like 10, 20 years. And especially at the tibia, there's not much out there. And so again, it's another area that needs to be explored.
I just know, I'm not sure if Sarah Mansky is here as well, but you know, she used a Botox injection into muscles and then looked at, I think, changes in bone mineral density. And I was wondering if they might potentially also have looked at, you know, change in bone shape when you introduce muscle weakness relatively arbitrarily, but maybe not.
Well, I mean, if bone is responding to forces that are being applied to it, the muscles are doing that application of force, or much of that application of force. So I could see that potentially resulting in maybe some changes in shape.
Yeah, the other thing I was wondering is, you said, you can use these markers, and if you have this shape modeling and it's more accurate, that would also help by using then similar markers or the same markers for movement analysis. But wouldn't be the big error in movement analysis be that these markers are not always exactly on the right landmarks, and they might move a little bit as you move? Wouldn't that be introduce a much bigger error than maybe the reconstruction of the bone shape that you have?
Oh, possibly. So when I talk about reconstruction from all those landmarks using motion capture markers, I would use the static trial. We wouldn't really do that during the dynamic trial. So it would just be to define those bone geometries, and then you'd use tracking markers to track the segments. And yes, there might be, we don't know what the errors are from the geometry estimation using the shape model compared to what the errors would be from motion capture. I expect they'd be a little bit larger than motion capture, but we don't know that exactly yet.
Another thing that I didn't quite understand was when you said that a wrong bone shape might also affect other things. For example, you mentioned moment arm calculations, and in kind of the muscle mechanics, when we want to know a moment arm, we usually use something called the tendon travel approach, which essentially, well, of course it depends on where the joint is and what your bones are, but you essentially don't look at bone shape at all, but you get it in a completely independent manner. And so I was not quite sure how bone shape would affect a moment arm in your area, like when people, like bone people, they use bone shapes to somehow get at moment arms, or?
So it's how it's defined in the musculoskeletal model. So if you were to change the insertion point or origin point for a muscle, or change its position in space, let's say if you increase the width of the tibial plateau or the condyles, you might increase the...
So you have a model with bone shapes that give you the moment arms, and then you change the size and stuff.
Yes, yeah. So
you have,
yeah, you have muscle insertion and origin points as well as wrapping points that are set on the bones. And so if those points change with bone shape, that's going to affect the moment arms in the model.
You mentioned the tibial tuberosity seems to be more prominent in males. Presumably that would give a bigger moment arm than if you use the smaller tuberosity and that type of thing. Yeah.
Yes, yeah, and I have used the tendon travel method, but it's just for some muscles you can't do that. And we're working with musculoskeletal models. You might have tens of 40 different muscles involved in the model, and you can't do the tendon travel method for all of them.
And I don't know anything about statistical shape modeling, but whenever I hear statistics, I always think of getting a heterogeneous sample is really of an advantage to kind of make correlations and the regressions and that type of thing. But you looked at a very homogeneous sample. Do you think that actually might have been a disadvantage in the particular approach that you used?
I think it would, if you have so that's one of the reasons we applied it to a new population, to the older adults, was to see, okay, I didn't include a wide range of ages, so I have a more homogeneous sample. How much is that going to affect the accuracy of the model if I apply it to a group that is outside of the variation that would be included in my training set? And so we did see increases in error. It wasn't able to account for all of the differences in shape, but the increases weren't all that big, and it still had very good accuracy. So I think for my particular application, that having a homogeneous sample was an advantage. And because it might have been in the previous papers that collected for those wide age ranges, maybe the larger errors were coming from the older adults, and reconstructing for the younger adults within that paper or within that group would have resulted in lower errors. And I just wanted to get a more accurate or more specific estimate of the error for younger adults.
Did you exclude subjects that might have had tibial or fibular fractures, or does that not really matter?
So again, we didn't, so we took healthy people. I don't think they were asked about previous fractures. I did exclude one participant who had very obvious evidence of Osgood-Schlatters. There's like a tunnel beneath, almost a tunnel-like structure below the tibial tuberosity. And so I didn't want to include that person.
The last question that you have to answer at one point, but maybe not right now, is you have to explain to me what jump rope competitions are and what you do in jump rope competitions.
That I can do. Videos are usually the best way to explain that.
You know, Walter, you were gone on sabbatical and Olivia presented this entire presentation on the biomechanics of competitive jump rope.
That might be recorded, actually.
Yeah, it's online.
Watch a video of how that works and what you do.
I see, Eric, you have a question for Olivia. Please go ahead.
Hi, Olivia. I think you did a great job today, especially your methodological slides. I know how tough it is to explain. I think that you did a great job with it.
Thanks.
My first question for you is, how much do you care about the fibula when most, let's say, stress fractures occur in the tibia?
Right, okay. So this goes to, I do care about the fibula, and I think EFOS would probably be able to explain his paper better than I could. I'll try to remember my best. But when you include the fibula in a finite element model with the tibia, it greatly increases the accuracy, or it greatly changes. I don't know if he looked at accuracy, but it greatly changed the stresses that you were getting, or in the distribution of stresses. And so including the fibula seems to be important, sort of as a strut for the tibia. So I can't say exactly how much it would affect it, but I do think it would. Oh, and Brent says stress fractures are common in the fibula as well. I did not know that.
Could I jump in, Olivia, for that one?
Yes, please do.
Yeah, so basically, Olivia's got it exactly right. What we found with the finite element model is that when we didn't have the fibula, it bent funny. So it bent in a pattern that didn't match real experiment. And the magnitude of the deformations were way too much. But as soon as we put that fibula in there as sort of a reinforcing structure, even though it doesn't carry a lot of the compression, it kind of helps keep the thing from swaying too much side to side, basically kind of reinforces it that way. So we found it mechanically to be very relevant, which makes sense. It means that you're not carrying around this extra useless bone, right? So it makes sense that it's there for a purpose. Sorry to jump in like.
No, thank you, Buzz. That's great. Yeah, and moving forward to, my eventual thought is that this will be applied where we can, I'm hoping to create finite element models from these statistical shape models once I am able to include density. And so we can start looking at, how does fibula shape affect tibial stresses and strains and things like that.
And moving forward, do you think that you'll do still so I understand for the question that you were asking today that you wanted to see how these structures scale together. But moving forward, would you do separate statistical shape models for both the tibia and the fibula so that you can get better, let's say, resolution on both of these individual bones?
That's something I'm playing with. I think I'll probably do both. And it might not all get written up, but I think it'll be interesting to take a look at. I'm also going to be looking at, do I do shape and density separately and then combine them afterwards so that I can manipulate those independently, or do I do them together and see if some are related? So
Thanks.
yeah, we're gonna do, there's gonna be a lot of modeling going on. It's gonna be great.
Thanks.
Yes, Tim, please go ahead.
Thanks, Olivia. I enjoyed your talk. Would you be able to include a sort of a time lapse feature into your model? Because you can now take young adults and map very nicely the structure. Would you be able to predict in the future what their bones would look like?
That's a very interesting question. I don't know. I think it would be maybe possible. It'd be really cool if you had the data set to look at that.
Yeah, I was wondering if you could take, you could scan an animal like a rat that never stops growing, and you could scan it at a juvenile and then get your statistical model to characterize it, and then kind of, at least in that animal, predict down the road what you think it would look like, and then go back and compare it to. I just think it would be interesting to know, because you do say that, the data, as people age, their bones do change shape. So I just wondered if you would be able to think about being able to have a predictive element to your model.
Maybe. I know that, I think if I had a really large data set over various different ages, I could look at, are there variations in shape that are related to age? And then maybe you could start to use that as a predictive model. I think it would get really complicated because you have so many variables that might affect that, nutrition, socioeconomic status, that sort of thing, activity. So it would be a very interesting question. I think it would be quite complicated in practice, but something to think about.
Okay, all right, thank you.
Emily, please go ahead.
Hi, Olivia. I really liked your example where you chose a set of landmarks that you think could be palpated and wouldn't require any imaging. What if you were doing IMU-based motion capture and you weren't placing any motion capture markers for a static shot? Do you think there's some manual measurements or measurements you could take from maybe like photo or video that could still give you some participant-specific landmarks?
Sure. So maybe you could do, well, we have segment length. So you could take like the length between sort of the head of the fibula and the lateral malleolus. You could take the length between sort of the medial condyle of the tibia and the at the proximal and distal ends. You could take the ankle width, you could take the ankle depth, maybe a distance between those lateral and medial knee markers and the tibial tuberosity. Those are the measurements that I could think might be relevant. I'm sure it wouldn't be as accurate as using the markers, but it could be a place to start. Another option would be, say, if for your study you were also taking like an X-ray, or if you had some deal with the manufacturers of the DEXA to get that raw data, you could, there are people that are doing 2D to 3D reconstruction from that sort of data as well.
Would there be any last question for Olivia? If not, I would like to thank Olivia again for sharing her work with us.